looked at the email that I sent you to see the relatively light week that you have ahead of you, okay? All right. So, your projects turned in already for all of you. So, boom, that's out of the way. All we have is two little things this week and a little test on Monday. Okay, so relatively light in that respect. We're going to talk about the last thing today, and then the rest of the week is going to be an opportunity for you to get some things done along with the review preparing you for the Monday test, okay? Also, at the end of the period today, we're going to talk about FRQ 21. Mary Martin's going to show us how to do the first part of that, and then we're going to move on from there since no one has turned it in yet. And then we'll... I understand, but a lot of people have not turned in a lot of FRQs, okay? So we're going to finish up on the last part today. It's called 23, concavity and the second derivative test. So that is what you would want to be pulling down from Moodle if you have not done so already, okay? Just as we begin into that, let's talk a little bit about the last thing that we talked about, which was first derivative test and critical points. All right, so let's refresh our memory, and I keep pounding this because we're about to make it get interesting as we talk about second derivative test here. Critical points are where what happens. Or what are critical points? Let's go back to that.
The derivative of the function is equal to 0.
First derivative is 0 or undefined. Okay? All right. What happens at critical points? The slope could go from positive to negative. Slope changes now. The slope changes to 0. That's all we can say for certain, bless you. Because remember, it could be that the slope is positive and then 0 and then negative. If we've got that, a positive then a negative, then a positive then a 0 then a negative, what do we know about that point if we have that scenario? If it's a positive slope, then 0, then a negative slope. What do we know about that point on the graph? It's got, look, it went from, there you go. It's a maximum, okay? It went from being positive to 0 to negative. What if it goes from negative to 0 to positive? What do we know? Then it's a minimum, okay? And that's the first derivative test. What if it's negative, then 0, then negative? It just whoop, whoop. It's neither one. It's not a max or a min. It just does it. What if it's positive, then 0, then positive? Same thing, okay? So that's a possibility for it to happen there. And all of those same scenarios with the undefined part of it, okay? And now, by looking at this, we use the first derivative test and these two scenarios right here to determine if it's a max or min. And what do we have to do in order to use the first derivative test? What do we call it when we figure that out? We draw out of what? A sign line, okay? So now that's all dealing with the first derivative and the first derivative test and finding out max or mins. Now, today we're going to talk about concavity. Where have you heard the word concavity before? With lenses, geometry. What does concavity mean? What does it mean to be concave? Curves. What word do you normally hear in other classes with concave? Convex. So what does convex look like? Anybody remember? Or what does concave look like? Yeah? Concave caves in. It's what you normally think of when you're talking about lens. Convex is like a mountain. Concave is like a valley, okay? We're going to use concavity and just say it's either concave up or concave down. Okay? So based on that information, where would you say this thing is concave? Well, where would you say this thing is concave at? The right side. I would say that it's concave here. And we're going to change that to say concave down. All right, and where would you say it is convex then? Or concave up? It's going to be concave up here. Ooh, let's try to spell just one word there, Ely. Spell it out in your head. Concave up, which is just another way of saying convex. But in math, we talk about concave up. It's concave up from here to here. All right? Now, here's this. Would you agree that this function is continuous? Would you agree that it is differentiable? Okay. Then this point here becomes an interesting point. Because that point right there is neither concave up or concave down. That point is where the concavity is changing right here. Now, let's talk about what's happening here. All right? Let's talk about what's happening to the first derivative. What can you tell me about the first derivative over any part of this graph right now? Can you tell me where the first derivative is positive?
Yes.
Where is the first derivative positive?
The first part of the slope before it goes down, and then at the bottom it starts going up.
Okay, so f prime, let's write it down here. F prime is greater than 0 from here. Is that what you're talking about to here? From 0 to pi over 2. And then from here to here. Now, I'm going to ask you a similar but different question. Where is the first derivative? What's my question? Where is the first derivative increasing? Let me write that down. F prime is increasing. What does it mean to be increasing?
It's from the bottom of the slope to the place.
From here?
To the blue line on the right.
So if we look at right here, and he says it's increasing from here to here. Why do you say that?
Because after the blue line is decreasing.
Okay, but how do you know it's increasing from here to here? Because the slope is what here? 0, and it's positive here, so it's increasing. All right, what's the slope right here? Negative something, would you agree? Well, it's negative something here, it's 0 here. Where's the slope increasing? Is 0 bigger than -1? So the slope is really increasing even all the way from back here? So f prime is getting bigger because somewhere in here the first derivative is -1. Then somewhere in here it's -0.75, it's -0.5, it's -0.25. The slope is actually getting bigger all the time in there. So f prime is increasing from pi to 2 pi. Okay? So f prime is getting bigger all the way from pi all the way over here to 2 pi. Now let's talk about f prime right here. Looks like it's a positive slope, but it's getting less positive all the way up here to 0, and then it's getting negative and more negative all the way to there. So f prime is decreasing from 0 to pi. Now, let's see if we can confuse you. Where is f increasing?
Between 0 and pi over 2 and pi over 2.
Okay? So you understand why I said the other day that it's important to get away from pronouns and say it is increasing, because we've got f is increasing over one interval, f prime is increasing over a completely different interval. Okay? Now, so that tells us that f prime was decreasing, then it was increasing. So something happened right there at this point called where the concavity changes. We're not going to prove it. You're just going to accept on faith. But this point right here is where the second derivative equals 0. Okay? Now, the first derivative is the rate at which f is changing. Right? The second derivative is the rate at which the first derivative is changing. So if you think of this as position, velocity, and acceleration, f double prime is acceleration. So let's go back and let's think about that, okay? PVA, this is position function that we've got graphed up here. Talk to me about the velocity from 0 to pi over 2. The velocity is increasing. Now, if the velocity is increasing, well, is the velocity increasing? The velocity is increasing. The velocity is it increasing or is it positive? Positive. Y'all think right here. The velocity is positive for sure, but it's slowing down, right? So I'm moving forward, but I'm slowing down. And then suddenly the velocity is 0 here at pi over 2. Now the velocity is negative. What does that mean about my motion? Which way am I moving if the velocity is negative?
You're moving backwards.
I'm moving backwards. So I'm moving backwards from pi over 2 to pi. What about my acceleration? I'm moving backwards at the second at what kind of a rate? I'm still increasing at a decreasing rate on. So I'm moving backwards at a decreasing rate. My velocity is negative. Wait a minute. Is that right? That's right. Am I right there? Okay. My velocity is positive. My velocity is 0. My velocity is negative. So I'm backing up from pi over 2 all the way to here. What's happening to my acceleration here? Well, since my velocity was 0, my acceleration's got to be something to keep me moving, right? I'm accelerating in a negative direction. Now, what happens right here? I'm still moving backwards, though, right? Because my velocity is still negative. I'm still moving backwards. But what happens at this point right here at pi? My acceleration starts slowing down. So I'm still moving backwards, but I'm moving backwards at a slower and slower pace, because what's going to happen at 3 pi over 2? That's when I stop completely. And now I'm going to start back moving forward. So my velocity is going to be changing, and my acceleration is both going to be changing. And we can figure that out by looking at the first and the second derivative. So let's look at in words what we just talked about, okay? If the second derivative is greater than 0, second derivative is greater than 0, then it's concave up. Now that's confusing. That's counterintuitive. So you've got to be sure that you understand that, okay? If the second derivative is less than 0, then it's concave down. No, that's not counterintuitive. Upward. Second derivative is greater than 0, it's concave up. Second derivative is less than 0, it's concave down. All right, the counterintuitive part comes in here at the second derivative test. Now remember this point pi that I said is where the concavity changes? Pi over here is where the concavity changes. That is called an inflection point. That is called an inflection point. Now please read the definition of inflection point and tell me how it's different than a critical point. What has to be true for it to be an inflection point? Second derivative is 0, so it's not first derivative, it's second derivative. Second derivative doesn't exist, but there's one other crucial thing for inflection points. The concavity has to change. Remember with critical points, we said if you're doing a sine line for the first derivative and the slope is positive, then 0, then positive, it's not a max, it's not a min, but it's still called a critical point. For inflection points, the concavity has to change before we'll call it an inflection point. That's a critical little thing that's different between critical points and inflection points. For it to be an inflection point, the concavity has to change. The concavity must change. That's a crucial piece that is easy to forget. Now, I want you to think about something here. Think about a function. And at a point, look at this information. I don't know what f of x is, okay? At x equals 3, f prime of 3 equals 0, and f double prime is greater than 0. Now, picture in your head, what does it mean if f prime at 3 equals 0 is flat? Okay? What does the fact that the second derivative is greater than 0 tell you? Okay? So at this point, we've got that the first derivative says that the slope is 0, and the second derivative says it's concave up. Tell me about that point. What can you tell me about that point? It's not an inflection point, but what about it here? Look at that. How would you classify that point there? No. Second derivative is greater than 0, it's concave up.
Yeah, but I thought it was the other direction because you said concave, like in the picture before. Concave down.
Oh no, I messed up. Yep. Yes, that should be concave up. That should be concave down. That makes more sense now. Sorry. Wow. Sorry. That was terrible of me. That was terrible of me. Yes. Concave up will hold water. Now this may make a lot more sense. Evidently, I did not prepare well for my class today. This will not hold water, okay? So if it will hold water, it's concave up. Yes, ma'am. Concave up is concave. Well, you're never going to see this word in here, okay? All you're going to see is concave up and concave down. All right, so let's go back. Concave up will hold water. This is concave up. This is a convex lens, if you're talking back in... Well, the up will hold water. See, if I pour water, it'll stay in that thing there. Okay. Okay. If it's up, The velocity is increasing, yes. Okay. Yep, it's going up. The velocity is going up. The velocity is going up. The velocity is increasing, right. If it's concave down, it won't. So, yep, sorry, I messed that up big time. Woo! Need to fire me and get somebody new in here. Okay, so now, if it's concave up, and the first derivative is, if the first derivative is 0 and it's concave up, that's a minimum point. Would you agree with that? Because it's going to, the slope of it's going to be like this. If it's concave up, it's got to look like this here or something like that. But it's got to be concave up. And if it's concave up, it's going to have to be a minimum. So what if you know that the second derivative, the first derivative at 5 is equal to 0, and the second derivative is less than 0? So think about what that looks like, okay? First derivative is 0. Concave down means it won't hold water. That means it looks like this. So this point then would be a maximum. This point would be a minimum. And that's called a second derivative test. So you can determine if a point is a max or min by looking at the second derivative instead of a sign line if you want to. So if you've got the first derivative and second derivative, you can look at those two things and determine if the point's a max or min. You can look at a sign line as well. Sign line will always work. Okay, you will not hear me say always very often in here. But a sign line will always work. Second derivative test will not always work. Okay? If the second derivative is 0 also, you've got to go back to the first derivative test. So the first derivative test will always work. You can always do a sign line and figure out if it's a max or min. Second derivative will tell you about the concavity of things. And that's the real place that we use the second derivative, is to determine concavity of things. So let's look at this function here. Lovely function. No one remembers what it looks like, and that's quite all right. Determine whether the graph is concave upward or concave downward without graphing it, okay? So what do we need to do algebraically to figure this out? Yes, sir? Take the first derivative. Will the first derivative tell us about concavity? No. Then take the second derivative, okay? How are you going to take the first derivative of this thing?
0, so you would end up with 0 plus 80 times 2x over x squared plus 2 in parentheses squared.
Yes, you can do low d high minus high d low, or you can bring x squared plus 2 to the numerator and make it -1, whichever way you want to go about doing it there, okay? If we do low d high minus high d low over the low squared, looks like it'll clean up to -16x over x squared plus 2 quantity squared. That's our first derivative. Does everybody agree with me on that? Okay, good. I haven't messed that up yet. So now, what can we figure out from that right there? What can you tell me just by looking at that? Can you tell me anything? Can you tell me what critical points are? Where is there a critical point at? Critical point at x equals 0. Is the first derivative undefined anywhere? No, because that denominator is always going to be a positive number. So we know we've got one critical point at 0. Okay? Now, let's go look at the second derivative now. Second derivative, we again got to do low d high. So low d high minus high d low. And what's the derivative of that? That's going to be 2 times that thing to the 1 times 2x, isn't it? All over x squared plus 2 quantity to the 4th. Now, say that again.
Could we have factored out x in the beginning on the 16x?
Right here? Right here? No, because we don't have an x in the denominator. Since that's quantity squared, we've got to square it before we could do anything there. Now, I'll caution you, or I recommend to you, or I plead with you to factor this thing, to clean this thing up some before you go any further. It's going to make your life so much easier because we've got two terms here. This is a term in the numerator, and this is a term in the numerator. What do they have in common? They have the x squared plus 2 to what power? The first power, that's all we can take out. Anything else we can take out. Yeah, but all we're worried about is the numerator right now. Hopefully we can cancel something in a second. But we can take out a 16, right? You want to take out a 16 or a negative 16? It doesn't matter to me. Yeah, I think I'll take out a negative 16. I think it makes it easier. So if we take out a negative 16 in that, then in the first thing we're just left with x squared plus 2. Minus. That 16 is going away. That's going away. So we've got 2 times 2x is 4x. Over x squared plus 2. Say that again. Oh, yes. Thank you. This 2x times that makes that 4x squared. Thank you. So now, is there any other cleaning we can do here? Yes, we can combine the x squared and the negative 4x squared. Anything else we can do? That'll become negative 3x squared plus 2. What about this x squared plus 2 and this x squared plus 2 to the 4th in the denominator? Yep. Let's just make it to the 3rd in the denominator, okay? X squared plus 2 cubed. So this is what our second derivative looks like. I think that's as simple as we can get it. Now, how are we going to figure out concavity now? Set the top part equal to 0. Negative 3x squared plus 2 equals 0. Do I need to set the negative 16 equal to 0? No, technically I do, but I can look at it and know it's never going to equal to 0, so I'm not going to write it down. So, negative 3x squared plus 2 equals 0. That means 3x squared equals 2. X squared equals 2/3. So x is plus and minus the square root of 2/3. Okay? Now, here's where it's very crucial for you to know these are possible inflection points. We can't state that they are inflection points until we know if the concavity changes at them or not, okay? So now, how do we determine if the concavity changes? We're going to draw a sine line for the second derivative. You remember me stating that we needed to be sure we label our sine lines? So we've got the second derivative. We've got the negative square root of 2/3 and the positive square root of 2/3. Now, what are our factors for the second derivative? How many factors do you see? 2? 3? 3. I see negative 16. I see negative 3x squared plus 2. And I see x squared plus 2 cubed. I see 3 different things here. So I'm going to write them all down. Negative 16, negative 3x squared plus 2, x squared plus 2 cubed.
Could you put the x squared plus 2 cubed over 1 over that?
It's not going to matter. If it makes you feel better to write it as 1 over that, then it's fine to do. All right, now, the negative 16 is always negative, right? So let's just go ahead and write that in everywhere. Can everybody see that the bottom one's always going to be positive? Because the 1's always positive. X squared is going to be positive. We're going to add 2 to it, so it's still going to be positive, and we're going to cube it, so it's still going to be positive. So the only thing for us to worry about is that middle one there. How do we figure out whether it's positiveness and negativeness? Pick a number. What kind of number do you want to pick all the way to the left? What's something smaller than the negative square root of 2/3? Negative 2. Negative 2 squared is 4 times negative 3 is negative 12 plus 2 is negative. What's the number between those two? 0. 0 squared times negative 3 plus 2 is, so it's positive. What are we going to put bigger than 2/3? 1? Yeah, 1's bigger than that. 1 squared is 1 times negative 3 is negative 3 plus 2 is negative. So, since I've got a positive multiplied by a negative multiplied by a negative, the overall sign for the second derivative here is positive. What does that tell you about the concavity there? It's concave up, okay? The graph is going to be kind of U-shaped in here. Now, it doesn't have to be a perfect U, but it's got to have some curve to it, and the curve's going to be up. What do we know about in here? We've got 2 positives and a negative multiplying. So the sign of the second derivative is negative. So it is going to be concave down. It has some kind of down curve to it. And what do we know here? We've got a positive times 2 negatives, so it's going to be back positive. So it's got to, again, be concave up, something like this. So it's concave up from negative infinity to negative square root of 2/3. It's concave up from square root of 2/3 to infinity. It's concave down between those from negative root 2/3 to positive root 2/3.
So they are inflection points?
Yes, so these are inflection points. Both of these are inflection points.
You had like a positive, negative?
That's right. If it was positive, positive, negative, this one wouldn't be, this one would be. It'd have to be, it's kind of got to be circular. The graph itself would have to be circular because it's got to be concave up, then it's got to be concave on, so it's going to have to be more circular there, I think. It's a good question. I've never been asked that, so I don't know.
So it's like an S, kind of?
Yeah. If it was an S, I think that's what it'd have to look like. I think that's what it would have to look like. It wouldn't be a function then. It would be just a relation. It'd be x squared minus y squared.
So we'll never run into the case.
Oh, yes, because remember we have implicit differentiation? That ugly stuff? Yeah, it doesn't count. Okay.
Implicit differentiation?
Implicit differentiation applies to any relation.
So we don't know if they're functions.
That's right. Well, in fact, you know that if it can only be factored implicitly, it's not a function. It can't be a function. Okay, does this make any sense to us here? All right, we're going to skip the next one and go to an easier one for you to find the possible inflection points.
These are the inflection points of the original equation?
No, this is the original. Yeah, I want to.
We're finding the inflection points for the original.
Yes, we're finding the inflection points for this.
So can you find the inflection points of the first derivative using the third derivative?
Yes, you could. We never do that, but you could. Yes. You could, but we won't go there. No, we won't go there. So find your first derivative and then find your second derivative. Okay. Did I do that right? I did. Once you've done that, what do you need to do? You're already doing it, so keep on going. You're going to set the second derivative equal to 0. I know. How did you get your second derivative and my second derivative don't agree?
No, they didn't.
Oh, yeah, okay, you pulled it up. Yeah, yeah. Yes. I would go.
Pull out the 4 with it.
Yeah, if you pull the 4 out with it, I think it makes it easier there. Yes, sir? Good question. Yes, it's really not going. It's all about what you want to do there. I know that doesn't answer your question, but let me explain. You've got to account for all of those things in there. So you could. Yeah. I would leave it as 4x and it's 5x squared minus 6. I would have those as two factors. If you wanted to list 4 as a factor, x as a factor, and 5x squared minus 6 as a factor, it's not wrong. As long as you've got everything listed there. Okay, so we're going to do a sign line. Smaller than that's -10. That's going to be negative squared. Yes, I have as my factors 4x and 5x squared minus 6. Do y'all agree with me there? Those that have finished, okay. Oops, I did not label this thing. Now, once you finish that, I want you to go and do a sign line for the first derivative. A sign line for the first derivative. That's probably going to be easier. Yes, sir.
May I use the restroom?
Yes, you may.
Thank you.
Bless you.
-1 is smaller than
Is in here? I think -1 is in here, yes. Is between these two. Yeah, that's the next fun part. Can you figure out what that graph might look like? Just based on what you know here? See if you can figure out just a basic sketch of this graph armed with the information that you have there. Oh, y'all talk about it. Talk with somebody about it and see what y'all think. I'm gonna hide the screen and go up here and actually graph this puppy and see how close y'all come to it. Compare it with somebody close to you there. See what they think. What you think, sir? Okay. Similar modeling. Okay. Wow. Wow. I must say, I am rather impressed with what I see, because that's what the actual graph looks like. Now, based just with the information that you have, you've got no way of knowing how high or how low anything is. So I don't expect you to have that in there, okay? But all of you had a basic shape that looks something like that. You should feel proud of yourself. You did not need that $80 machine to figure out what the basic shape of this thing was.
What is the second derivative?
Think of second derivative as acceleration. The second derivative tells us that this thing is concave down from here all the way to right along in here somewhere. It'll hold water. And then somewhere in here, it starts curving a little bit. See, it'll kind of hold water there. And then here, it starts back curving down, but then right along in here somewhere, it starts back curving up, and it'll hold water again. So if you're thinking that my velocity is positive, I'm going real fast, but I'm slowing down, now I'm going backwards, and then suddenly I'm going to stop in here, and my acceleration is going to start back forward. So I'm still going backwards, but I'm going backwards slower. Then right in here, I am sitting still and not accelerating or anything here. And then suddenly, I start going forwards because my velocity, I'm going backwards, I'm sorry. I start accelerating backwards, so I'm going backwards. Now let off the accelerator, so I'm still going backwards. I'm rolling backwards. I'm going slower. I get to 0, then I hit the gas hard and I'm moving forward.
So it's really just like stretching the sun wave.
Yeah.
Stretching the sun wave. When you look at it like just with your little sign, I guess your sign line, it's only a sign graph.
Yes, your sign, S-I-N graph.
It's like up and down, and then you just stretch it however.
That's right. That's what, once we figure out these exact values, then we can stretch it and see what things are doing with it there, okay? All right, I don't want to go any further with this stuff today. I want to take just a moment. I'm going to move assignments off one more day, okay? The 8, homework 22, I'm going to move it one more day because I want us to have another day to talk about this. But I do want Marty to come talk through the first part of this for us because I think quite a few of you are having difficulty with this. Oh, you can do it all if you can. Okay. Well, see if you can talk through the first part and y'all ask your questions there. Okay.
Oh my gosh!
What?
Oh my God, you're right.
And tell them how you got that. Not Mr. Ely told you.
But since they're perpendicular and it's negative.
So they have to multiply to give you -1. No, the slopes have to multiply to give you -1. One could be 2 and one could be negative 2 and 1/2, 2 and -1/2, 3 and -1/3, 7 and -1/7. Okay, tell us where you got that from. Step aside so we can see it over here. All right, do you see why it's a -2kx of 0 the second time around? Because you're putting a -x of 0 in there. And that's the first derivative at both of those places. So what has how is the first derivative related to the slope, class? They're the same. So continue on. Tell us what you're going to do from here.
So now I'm just doing this, where I multiply the two derivatives together and then get x to the y.
All right, so go for it.
Wait, is there a way to extend the page?
Yes, over on the right side, you can pull the bar down. Yep, that thing right there. And then you can hit extend page. There you go. And you're solving for x of 0. Okay. Okay. What y'all think? I think she could argue that she was right without the plus minus there. Why could she argue that she's right if she just puts the positive one?
What was the original problem? Oh, because you're looking for the original.
You're looking for x of 0 and negative x of 0. So if x of 0 is 1 over 2k, then negative x of 0 is negative 1 over 2k. If x of 0 is negative 1 over 2k, then negative x of 0 is negative, which is positive. So I think you could argue it either way. Writing the plus and minus is not wrong, and that's where I would go from there. So now, B part says find the slopes of the tangent lines mentioned in A. How do you find the slope of the tangent lines?
The first derivative.
Okay.
We know what k is, we just insert that in,
But we don't know what K is.
Then we find, we know what x is in terms of k, so we can substitute that in for x.
Very good. If you go down to what she did, you know what x of 0 is. If you put x of 0 into f prime, you'll figure out what the slope is. Does everybody follow me there? All right, so I'll leave that for you to do. Find the coordinates in terms of K and C of the point of intersection of the tangent lines mentioned in A. What does that mean? Find the coordinates in terms of K and C. What on earth does that mean?
It means where the two lines.
No. Just to find the coordinates in terms of K and C. What does that part mean? Not necessarily. K and C are going to be in your answer. So if you have K's and C's in your answer, it's okay, is what we're saying there. So, it's okay to have K's and C's in your answer for C part. So I want you to go back and do B, worry about C a little while, and then we will move on from there tomorrow, okay? So, what I want you to accomplish right now, you've turned in your related rates project, okay? This concavity homework, I'm probably going to put off until tomorrow. This has already been put off until Wednesday, so I'm not going to move it. But you can do some of this WebAssign 13 already. Anything that talks about just the first derivative, you're capable of doing now. So I'd recommend working on the FRQs you haven't turned in. I'd recommend working on the first part of this WebAssign tonight and flustering a little bit with that FRQ. Now, we are only planned to have AP help in here this week on Wednesday. I have no idea why I planned it that way, but I did. I'm sorry for that. So you probably want to, I think I'll ask Mr. Autry about, I'll talk with, well, y'all need to use your time wisely this week. If you need to stay here, you might need to stay here and get some suck-up points one day during the second period instead of going down there for the suck-up points one day. But that's your decision to make on that. But we are going to have it on Wednesday of this week. So, what are you supposed to work on tonight? Work some on WebAssign, work some on FRQs, and we'll continue with concavity and the second derivative test tomorrow. Any questions? All right.